Hello and welcome back to Dynamic System Modeling, in which we will continue our discussion about Laplace transforms. As we mentioned in a previous session, we will use the table which make things easier for us. So if you are given the function f1 of t equal to t squared, you can use the equation which is 1 of fs in order to obtain the Laplace of f of t, which is the Laplace of f1t is equal to the integral from 0 to infinity t squared e power minus st dt, and you do the calculations to obtain it. Alternatively, we can use directly the table, in which it's given that the Laplace of t squared is given by 2 factorial over s cubed. So f1 of s is equal to 2 factorial, which is 2 over s power 3. Let's do another example. If we have f of t of t is equal to e power minus 2t cosine 3t, we can see that the same equation is given in the table, so the Laplace of this term is equal to that. So f2t of s is equal to s plus a, the exponent over the exponential, s plus 2 over s plus 2 squared plus w or omega squared, which omega is equal to 3, which is 9. Okay? So if the equation now is given as f1 of t is equal to t e power minus 2t cosine 3t. If you look on the previous table, we could not find any formula that looks the same. However, on the second table, it is given that tf of t is the Laplace is equal to the derivative of f of s by ds. So if we assume this is f of t and this is t, then tft, the Laplace of it, must be given as minus df of s ds. Great. So f1 of s is minus d by ds of the Laplace of this term, which is given by this one, right? S plus 2 Now, doing the derivative of this function, I could remind you that u over v prime, it is u prime v minus v prime u over v squared. So great, this is the Laplace of f1 of t. Now what if we have a differential equation? So let's assume that we have a first order differential equation and the input f of t is a unit impulse function. And the unit impulse function is equal to 1 at time equal to 0 and 0 otherwise. If you want to plot it, this is the t, delta t. This is how the notation is used for the impulse unit, for the impulse function. So it is 1, the unit, it is the magnitude of it, it is 1 at time 0 and 0 otherwise. So in order to obtain the Laplace of this, we will be using the table. So f dot of t, the Laplace is given as f of s minus f of 0. So this is s ys minus y0 and this is f of t is a unit impulse function which is given by so the impulse, okay, let's see, okay, it is 1, right? So 1, the Laplace of f of t is 1. Great. So here you end up finding the Laplace transform of the first order differential equation. Now the objective is to determine actually y of t. Simply, you can do the opposite. So you search for the s domain and try to figure out the time domain. So y of t, so the inverse of this, okay, so we will search, okay, it is 1 over s plus a, it is e power minus a t. So this is equal e power minus 1 t over tau plus y0 e power minus t over tau. So this is the time domain, and this is called the inverse Laplace, which we will discuss in the upcoming section. In order to have a practice on a real dynamical system, let's take the electrical system. So first of all, we will write the governing equation. We could take the E0 as a node, okay, and this is the ground. Then E0 minus EI over R plus okay. So now we can obtain directly the Laplace transform of this equation, and given that the initial conditions are equal to 0, so there is no excitation current at t less than 0, okay, so this is equal to 0. Great. So the Laplace transform of this is equal to 1 over r e0s minus the input. Let's assume that the input is an impulse function of magnitude a. So you have like 5 volt, 3 volt, I don't know, some magnitude a. Okay, so it would be a over s, right? Plus 1 over l. The integral, so the Laplace of the integral is 1 over s, okay, multiplied by 1 over s f of s, which is e0 s equal to 0. Great. So e0 now you end up finding the Laplace transformation of the governing equation of this electric circuit. It is given as by some constant s plus a, so there is no coefficient beside s, so we should remove it, right? So we divide by l, so dividing up by l, it ends up by a s plus r over l. Now if we want to find the time domain of this, we perform the inverse Laplace, then we can find E0 of t, the output, which is what we want to find. E0t is equal to a, the constant, e power minus r over l t. And this is from the table. Now let's have another system. So we have this mechanical system. So we draw the free body diagram after assuming that the motion is given to the right. So this is the input. Okay, again assume it is a constant, like some constant A. Okay, 5, 10 newtons, whatever. Okay, the D'Alembert law mx double dot and px dot. Then we have mx double dot plus px dot equal A. We perform the Laplace. Okay, of x double dot, it is given by s square f of s minus s f of 0 initial condition minus f of 0 dot. Now the initial conditions are set to 0. Alright, now we get the Laplace transform of this second order differential equation, and if the objective is to find x of t, okay, then if you look over the table, it's difficult to see or to find something similar to this equation. So on the next session, we will cover how to obtain the inverse Laplace for such functions. Good luck, thank you.